Welcome back to the Code Search channel. In this video, I want to talk about a famous method for object detection. Although this paper was published in 2001, we see that this method is very practical. Before implementing this paper using OpenCV, I want to briefly discuss important parts of this technique. The basis of this method is using some kernels known as Haar features. So we shift these kernels on our image, and for example, we subtract the sum of pixels in the white part from the sum of pixels in the black region. And later we investigate whether we can identify a particular feature in our image, such as a part of a face. This article analyzed and trained several kernels on many face images and realized that these two features are very useful in detecting faces. If we look at the eyes region, we can see that it is darker than the below part. The second feature is for identifying a line, and again, the eyes region is darker than the nose area. But in order to address the high computational burden of calculating the sum of pixels associated with each kernel, this paper utilized a cool approach. It used integral image for obtaining the sum of pixels in rectangular areas. To calculate each pixel in our integral image, we sum the pixels that are positioned up and to the left of that particular pixel. For example, let's see how we can find the sum of pixels in this region. Number 46 is showing the sum of pixels in the orange rectangle. Next, we should subtract the sum of pixels in this green vertical rectangle, that is 9. This blue horizontal rectangle should also be subtracted from our sum, that is number 12. Finally, because I have subtracted this pixel with a value of 4 two times, I have to add it to my result. Now let's see how this paper could identify useful kernels for detecting faces. This article used adaptive boosting. In this method, a linear combination of various features known as weak classifiers is used. Similar to a decision tree in this method, based on only one feature, we divide our equally weighted dataset into positive and negative images, for example, faces or not faces, and we select the feature that has the best performance in dividing our dataset into positive and negative instances. In the next step, we increase the weight of instances that are wrongly classified and repeat the classification process. Finally, we have n classifiers that work together and generate an ensemble method. After calculating this value, the strong classifier decides, for example, if a particular image is a face or not. Finally, to speed up the process, this article used cascading. In each stage, this paper used several features according to their importance. If during this process one of the stages fails to detect the face, it terminates the process and outputs the result. For the first stages, it tries to detect all faces. In other words, it used thresholds to minimize false negatives. On the other hand, as we move further through the stages, more complex classifiers are used to decrease false positive rates. It is clear that all stages should be passed in order to detect a face in an image. Now I want to implement this method using OpenCV. First, I import the required modules. I load the trained face and eye detector models. Let's have a glance at these files. Here it is showing that we are using adaptive boost. Here we have the kernel width and height. We have 93 features that are distributed in 24 stages. And for each stage, we have thresholds for deciding if an image has eyes or not. I create a window with the window normal flag so that I can resize it later. Now I load several images, then convert them to grayscale. Now, with the help of the face detector, I try to find faces in my images. The first input is my gray image. The second input is a scale. As I've shown earlier, we have trained our model using a specific kernel size. Therefore, we have to resize our image in some steps so that the model can detect faces. For instance, I use 1.5 to create my pyramid images. Next, I should specify the minimum adjacent rectangles to a detected face. These are hyperparameters that we should select based on our image. To limit the number of detected faces, I select 3. Later, I will change these parameters in real time. Now I have the coordinates of the detected faces. I can draw them on my images. Let's see the results. Now I use my eye detector to detect eyes. For the second part, I use the body detector. I read a video file using OpenCV. I iterate through the frames and convert them to grayscale. For this time, I use a trackbar to adjust my hyperparameters in real time. For the scale option, I create a scale option in the setting window. Its current value is 1 and the maximum is 100. The final input is a callback function that is triggered when we change our trackbar. I repeat the same process for mean neighbor. For the callback function, I just create a sample function. I get the scale value using the getTrackBarPosition. For the scale value, I should map the value to a continuous value. I use interpolation from NumPy and map values to a value between 1.05 and 6. And to check the values, I write them on the image. You can see that we can change these parameters based on our input video. So that's it for this video. I hope you find this video helpful.